Okay, hello everyone. We are back and we are going to continue with vitamins, and we are going to talk about the B complex. So you just have finished exam number 1, and I want to congratulate everyone because I think overall the results are pretty good. The average is pretty high actually, and I think you did well. So I hope we continue the same path all the way to the end. So again, we have the B complex to discuss now, and we have 8 vitamins. Let's do 3 of them today, B1, B2, and B3, and then we'll continue in the next classes. We'll finish the other ones. So to begin with, we'll talk about vitamin B1, or thiamine. So actually this was the first vitamin discovered, and it was related to a condition called beriberi, which is a disease that results from the deficiency of thiamine. And thiamine, there are 2 sources of it. You have it from plants. We call thiamine, that is free or non-phosphorylated form. And we have it in animal products. We call thiamine pyrophosphate. It's almost entirely in the phosphorylated form, and it's bound to proteins. Basically, in the animal form, it's inside of the cells, and once it gets in the cells, it binds to certain proteins. So it's what we call phosphorylated form. So 2 different sources you can get thiamine, or vitamin B1. This is the way how the molecule looks like. So this is the thiamine, the plant derived one. So on the left, so it's thiamine, and you can see here the thiamine pyrophosphate. On the right is you have a phosphate group attached to it. And obviously, because of the presence of this phosphate group, before it can be absorbed, it needs to be partially digested. What do I mean by this? This phosphate group has to be detached, or it has to be cleaved, separated from the thiamine molecule, and then the thiamine free thiamine can actually be absorbed. So it requires some digestion in order to be absorbed. Again, digestion meaning that you remove the phosphate group only. You cannot modify the rest of the molecule, because then it loses its biological activity. So it can also be destroyed if you expose thiamine to heat. So cooking can cause loss of the vitamin. So usually the best sources are the ones that you don't cook, or you don't expose to heat before you eat. So for that reason, probably you're going to get more easily the requirement from plant-derived sources, provided that you don't cook them, or you eat them raw. But these are the 2 sources that we usually get from foods. So what are the primary functions of thiamine? It works as a coenzyme, so it's important for energy transformation and for the synthesis of pentoses and nicotinamide adenine dinucleotide phosphate, or NADPH. I'm sure you've heard of NADPH, because this is an important molecule that is used to synthesize DNA, or for biosynthetic processes in our cells. So, and it's also crucial for energy metabolism. And in a non-coenzyme capacity, thiamine activates chloride transport in nerve membranes, and for that reason it's involved in nerve impulse transmission, and regulates sodium channels and the phosphorylation of proteins. So it has a variety of functions which are crucial for maintenance of normal health. So what's the recommended intake? So thiamine, the RDA for men is approximately 1.2 milligrams per day, for women 1.1, and the slight differences because of body size, but not very different there. I would not even consider the 0.1 milligram difference really a relevant thing, but that's what the RDA says. So what are the dietary sources? Where do we get them from? Animal products in general, but pork and eggs are probably the most the richest ones, but you get it also in plants such as in oatmeal, wheat, especially whole grain, black beans, wheat germ, soy milk, fortified cereals, enriched rice and pasta, asparagus, green peas, tuna, legumes in general. So you can see that there is a wide variety of foods that can actually provide vitamin B1. So other symptoms of deficiency. So as I mentioned in the beginning, beriberi, which means weakness. Berry means weakness. And it was a disease that, again, nowadays it's not as common to find anymore because people can, again, as I always mention, unless you are in those countries or living in places where you have extreme poverty or limited access to food, very rarely you see deficiency of vitamin B1. So, but if that happens, it's characterized by fatigue, apathy, atrophy of the legs, peripheral neuritis, decreased memory, confusion, irritability, and muscle weakness. Remember, because thiamine is important for energy production, so if you don't have it, fatigue is a symptom. Apathy also, because it can also affect how active you are on a day-to-day basis. Causes atrophy because the muscles become weak. Can also affect your nervous system, so peripheral neuritis is related to that. So memory, confusion, irritability, these are all symptoms of the effects of the lack of thiamine in the central nervous system or in neurons. Toxicity. So non-known is not a vitamin that we hear of people taking too much. However, there are some cases where pharmacological use, you give high doses intravenously, so you have to actually inject in a person. In some cases, when people cannot eat or they are unconscious or they are in the hospital in a condition where they cannot voluntarily eat, so they have to be injected with vitamins or with any compound. So in this case, it might cause toxicity, but other than that, is almost unheard of. So it's been associated with headaches, convulsions, cardiac arrhythmias, and anaphylactic shock. So, but that's mostly if you have to give it intravenously, because by oral consumption, we don't have any reported symptoms of toxicity. So the second one, the other vitamin is B2 or riboflavin. In biological systems, riboflavin is usually phosphorylated, and it's in the form of flavin mononucleotide or FMN, and also flavin adenine dinucleotide or FAD. I'm sure that you've heard of NAD, FAD. So in this particular case, we are vitamin B2 or riboflavin is a main component of this compound. So it's stable to heat. So when you cook foods, you don't lose activity of riboflavin, but it's very sensitive to light. So as long as it's in it's inside of the food, or it's prevented from exposure to light, it should be fine. And in most cases it is. So how does the molecule look like? So riboflavin or B2, it can be divided in two parts here. We have on the left side, which is the head of the molecule. So it's the flavin or isoalloxazine, which is this cyclic compound here on the left. And we have a tail, or it's a ribitol tail. And this is what makes the riboflavin molecule. This is the combination of these two elements here, or these two portions, the head and the tail. And it can also, as we said, you can phosphorylate. And this is what we mentioned as flavin mononucleotide. It's a coenzyme, so it works as a coenzyme in cells. So you see here that we have one phosphate group here. So that's why it's called mononucleotide, because you have one phosphate group attached to it. And this is what happens inside of the cells. And then we have here the flavin adenine dinucleotide, which is also a coenzyme here, or FAD. And you see here that you have the the riboflavin molecule here, and then you have two phosphate groups attached and a nucleotide, so that's why it's called flavin adenine dinucleotide fat. So it's a much bigger structure, and this is what you see again inside of the cells. Once riboflavin is taken up by the cells, it can be converted into these two forms, these two coenzymes called FMN and FAD. It's widely distributed in foods, although more so in those of animal origin, because again it's inside of the cells that it's stored as FMN or FAD. So riboflavin is found mostly bound to proteins in foods, and it must be digested freed from flavoproteins in order to be absorbed. Again, if you eat a piece of meat and you have riboflavin bound to proteins inside of the cells, when you digest those cells, or you break down the cell, you have to actually separate the vitamin from the proteins that are bound to them, so then you can be absorbed. So it requires some degree of digestion. So when you eat, again, as I said, if you eat a piece of meat that contains riboflavin in its phosphorylated forms, either FMN or FAD, it has to be separated from the nucleotide, from the proteins, and then it can be absorbed. So liver, kidneys, and heart are the organs where the highest concentrations of riboflavin are found. The total body reserve of riboflavin in the adult human is sufficient to provide for the metabolic demands for 2 to 6 weeks. In other words, you have all these molecules trapped inside of the cells. So even though they are called water-soluble vitamins, you don't eliminate them because they are trapped inside of the cells. What happens is, as they are degraded, or cells are recycled, or you have broken down of these compounds inside of the cells, then you need to recycle. But in general, you have enough stored inside of the cells or trapped inside of the cells that would be sufficient to sustain the demands, or to meet the demands of the cells for 2 to 6 weeks. So you won't see easily a deficiency, or you don't become deficient very easily, because you have a certain amount of this vitamin that is trapped inside of the cells. And again, and once inside the cells, riboflavin is converted into its coenzyme forms. There are two enzymes. One is called flavokinase, that makes the FMN form, and FAD synthetase, that makes the FAD form of this vitamin inside of the cells. Primary functions, as the name says, they are required as coenzymes for carbohydrate and fat metabolism. So they participate actively in the metabolism of carbohydrate and fat, either to generate energy or for other intermediary metabolism steps of fat and carbohydrate metabolism. So what's the recommended intake? So for men is 1.3, for women 1.1 milligrams per day. Again, the difference is because of body size. Men in general are a little bit bigger, so they require a little bit more than women, but the difference again is not that big, and I think it's not really a major issue in terms of acquiring, or that you need to eat a lot more or less if you're a woman, because it's very similar to what for both men and women. Now, if a woman is pregnant, then the requirement is also higher, and for obvious reasons, because you have women producing milk or breastfeeding, they have to feed during pregnancy. There is a higher requirement because also of the growth of the baby inside of the womb, but also after pregnancy when breastfeeding happens, so it also has a higher demand for riboflavin. So in this case, it's 1.6 milligram per day. It's pretty much significantly higher for pregnancy and lactation, obviously in women. So what are the dietary sources? Milk, for instance, is 0.45 milligrams per cup if it's a non-fat milk. Yogurt, 0.48 in a cup. Egg yolks one egg yolk is approximately 0.26. Meats in general, 0.11 to 0.25 in 85 grams of meat, which is not a large amount. With liver being particularly rich, if you were to pick a food, you want to get all the vitamins, all the best, probably the richest food in terms of nutrients you can get, not only in terms of vitamin, but pretty much everything. Liver probably is the food that has is the best option. If you were to pick only one food, if you were allowed to eat only one particular food, you had a choice, probably liver. And if you were to make your decision based on nutritional value, probably liver would be the choice. But I know that people, usually when you talk about liver, people, liver is not the most appetizing food. Some people love it, but a lot of people don't like it. But in other words, it's particularly rich in riboflavin. You also get it in enriched bread, cereals, and grains. So these are processed foods. These are industrialized foods. They can also contain some of the vitamin, but that's because it's added, it's enriched. So what are the symptoms of deficiency? It's called, not common again, but in case it happens, it's called riboflavinosis, or lack of riboflavin. So you see swollen mouth and throat, and seborrheic dermatitis, and anemia. This is again associated with fat and glucose metabolism, inability to really process them properly, and also because resynthesis of membranes and recycling of cells can also be affected. And in this case, it can also lead to anemia. Toxicity, none known. So there are no reported symptoms of toxicity with riboflavin. The third one is niacin, or vitamin B3. So originally discovered in association with a medical condition named pellagra in humans. So you can see that most of these vitamins, they are discovered because at some point in time people were deficient of them, and trying to discover or find out what was causing that particular condition, vitamins were discovered. So all of them have some relationship to a particular condition, disease, and then understanding how the disease was caused, then the vitamins were discovered. So pellagra, particularly for vitamin B3, which is a disease characterized by what we call 4 Ds. These 4 Ds are dermatitis, so it's the skin problems, diarrhea, so inability to really retain anything in your gut, dementia, because it affects the brain, and ultimately death. So dermatitis, diarrhea, dementia, and death makes up these 4 Ds that are typical of pellagra. As you can see, a very serious condition that can lead to death. So how does the niacin, or vitamin B3, look like? So we have 2 forms here. We have the nicotinic acid, which is the left form here, which has a hydroxyl group attached to it here in red. And you have also the nicotinamide, that you have a amino group attached to it. So in both cases, they are active forms of vitamin B3, but one we call nicotinic acid because it has an acidic, this is a carboxylic group here. I said hydroxyl here, but actually you have a carboxyl group here, and this is what makes it acidic. And you have a amino group that is what makes it a nicotinamide, right? So, but both of them with full vitamin B3 activity. Now, nicotinamide can be bound to, is bound to a ribose, as you can see here, and also to a phosphate group, to a nucleotide. And then if that's the case, we are going to have the nicotinamide adenine dinucleotide phosphate. So if this, in this part of the molecule, in the adenosine part of the molecule, you have this R in purple here. If you have here this phosphate group, then you form the nicotinamide adenine dinucleotide phosphate, or NADPH. And if you have a hydrogen at this, replacing this R here, you have what's called nicotinamide adenine dinucleotide NADH. So these are two different forms of NADPH and NADH that require for the formation of this inside of the cells. Again, you absorb the B3 vitamin, either nicotinic acid or nicotinamide, and then what happens is that inside of the cells it can be assembled in this much bigger molecule, and it can take two different forms. One is the NADPH, if it has a phosphate again at this, replacing this R in this portion of the nucleotide, or NADH if you have hydrogen replacing this R, this radical here. So this is the main forming side of the cells. So in animal foods, niacin is found mainly as NAD and NADP. In plant foods, niacin occurs mainly as a nicotinic acid, again because in plants you don't need to form that molecule, that structure. So in plants you have a smaller or form of the molecule that is independent of the other components that are attached to it. So niacin is fairly stable in foods with minimal losses of the vitamin from cooking or storage. So it's a pretty stable vitamin. So what are the primary functions of niacin? So as a coenzyme, it assists in the metabolism of carbohydrates and fatty acids for energy production, as well as in the fatty acids and cholesterol synthesis. Niacin also plays a role in DNA replication and repair in cell differentiation. So you can see it has a very important role in maintenance of normal cell function. So either for energy production and synthesis of molecules that are part of the cell, but also for DNA replication. So if a cell is dividing, it requires niacin because you need to replicate DNA for cell division. So for that reason, it's important for cell repair and differentiation. Replication, repair, and differentiation. So what's the recommended intake? Men and women, again, men 16 milligrams per day, women 14. The upper limit is approximately 35 milligrams per day. And in lactation, it's here it says 1.6, but in fact it's 16 milligrams per day. So for women, obviously, it goes from 14 milligrams per day to 16 milligrams per day. I'm going to actually fix this. What I'm going to do is I'm going to take this out. Okay, good. Okay, so it's 16 milligrams per day during lactation. So breastfeeding always puts an additional demand on all nutrients in general, but it wouldn't be different with vitamins, in this particular case, niacin. So what are the dietary sources of niacin? So again, liver, beef liver, it's approximately 15 milligrams and 85 grams, so you pretty much get the entire amount that we require in a day if you eat one serving of beef, of liver, in this case, 85 grams. And most cuts of meats in general, they are all rich in this vitamin, in niacin. So chicken breast, you get approximately 12 milligrams in 85 grams of chicken breast. Salmon, 5.7. But you can also get in foods that are considered processed foods, but they are enriched with vitamins, and niacin is one of them. So Cheerios, you get approximately 5.7 milligrams in 30 grams of Cheerios. Cornflakes, 6.8 in 28 grams. So you can see it's enriched. So with relatively small portions of these foods, you can also get almost all you need in a day. So you also have in enriched breads and grains, canned tomato products. So not hard to get. As you can see, not not a, I would say it's difficult to develop deficiency, unless again you have no access to food, or you are in this particular situation where you are deprived of food for a long period of time. Not common nowadays. So symptoms of deficiency is the pellagra, and it's those 4 Ds that we mentioned before, but it's also vomiting, constipation or diarrhea, and apathy. Given the complexity of functions that this vitamin has, it can really have devastating effects if you're deficient of it. Toxicity, there is this called flushing of the skin, which is the redness of the skin. There is this red coloration of the skin, so it's flushing. Looks like there's more blood flowing in a particular area. So that's what we call flushing of the skin or redness of the skin. It can also cause liver damage, glucose intolerance. You have difficulty in processing glucose, and so then it accumulates in your blood. So it looks like it ends up being classified as glucose intolerance, but it's because you're lacking a major coenzyme that is important for metabolism of glucose. Not only glucose, fat, lipids too, but glucose is typical because cells use quite a bit. And if you take a lot of glucose, but if you have an abundance of glucose in the system, but you cannot process, you end up accumulating it outside of the cells, and it can be classified as glucose intolerance. But it can also affect vision, so blurred vision, and inability to really, when you look at things, but you can't really differentiate the image. So blurred vision and differentiation of vision. So these are typical symptoms of toxicity if you take too much. Not common though. Again, it's not a. You have to take a massive amount. You have to supplement, usually not through foods, but normally if you take supplements, that's when you may develop some degree of toxicity here. But commonly, it's an uncommon, it's not a common thing to see. Okay, so we are gonna, our next class, we are gonna talk about 3 more, and we are going to start with vitamin B6. So for now, thanks for watching, and I'll see you on Friday. So today this lecture is the first one after the exam, and again, good job guys. Keep studying, keep reading, and we'll talk soon. Bye for now.